Shall we start on time? Okay, my name is Andy David Hazy, and I used to be at RIT where I tried to teach for 45 years. It was a good run. I had a good time. I miss my students. I shouldn't have retired. But the politics got to me and I walked out the door. However, I do miss my students, as I said, and I guess you all will have to kind of substitute for them for this hour and the period of time that I spend here tomorrow also. So it's kind of fun for me to do this. It reminds me of good times. And the topic that I was connected with at RIT was technical photography. Not too many places that offer courses such as the one that I did. Technical photography is sort of specialized applications of photography to solving problems in technology and engineering and science, and not so much about art. So I understand, and I've talked to teachers in the past. I'm not a high school teacher, and I don't have experience teaching with a lesson plan and having a curriculum set out. The truth is, as time passed at RIT, lesson plans for me went out the window. You know, I cut off the seat of my pants as I walked in the door. So, you know, you do have some freedom that way at RIT or at a university, and that's kind of fun. But I was actually a fish out of water. I mean, the school was primarily an art photography school, and I was teaching technology. But it's okay. Some of my best friends are artists. So I would like to start this discussion by kind of pointing out some of the things that I don't do. And yeah, right. I pulled up the wrong set of pictures. It doesn't matter. We'll shortcut this because I brought up, I'm not sure how many of you were here last year, but if you were here, I don't want to really bore you, but if you weren't, I want to show you one demonstration that has kind of popularized my approach to teaching and approach to problem solving with simplified equipment. So, let's see. Photography is sometimes thought of as making pictures of things like this, right? Or pictures of things like this, or pictures of things like this. But then there are other situations where regular camera is just not good enough. And one of those might be, you make pictures like this. Astrophotography. I have a favorite saying about astronomers: they're glorified photographers. And the reason I can say that is because most of them don't put their eye behind an eyepiece. What do they put behind the eyepiece? A camera. And then they look at the images. So aren't they making pictures? And photographers. Yeah, that's right. They don't like me saying that. Sometimes there are situations that call for a solution which is not really apparent to an average photographer. Taking a picture of the space rocket shuttle trail as it lifts off is not something that you just pick up on any old, even digital camera and say, oh, yeah, I'll do that. And it'll come out like this. You got to think about it.
Time exposure.
Or you might want to do a photograph which is a multiple exposure. You could say, well, some of these things you could do with Photoshop. You know, Photoshop is a solution to all special effects. Grant you, but sometimes it'll take you a lot longer to do it that way if you're interested. Photographs of special situations such as this. How do you photograph a wasp in flight? It takes more than just a camera. It takes a special system that you have set up to make sure that the wasp is in the right place at the time you take the picture. Or you can kill it and glue it, right? Ingenious solutions are okay. That's in my book. Stroboscopic photography. You know, these days, this becomes easier and easier. Even iPhones can do things sort of like this.
They're actually coming out with cameras that have embody multiple exposures again now because people are
Right.
It's so difficult to do it in Photoshop.
That's it. But they still come with other problems. But then you have situations that again call for what I call applied photography. A regular camera, but a special optics that allows you to visualize heat gradients or temperature gradients in air, such as warm air rising from my hand, on the top of my head right now, because it's pretty hot. How do you go about doing that? You know, well, it takes a little bit of thinking. Or polarization, stress analysis in crystals and plastics and so on. It takes a little extra knowledge than what it takes to make a technical knowledge, than it takes to take an artistic photograph. In my belief, or whatever, I think that photography is part technology and part art. You can create great art but have no way of duplicating it, or you can create great technology but your photographs stink. So it's good to have an appreciation for both. And I like to say to students is, you know, don't go study photography necessarily. Study something, but then apply photography to what you're studying, whether it be engineering, surgery, whatever. And you'll be better for it. A better communicator, and a better researcher, a better engineer, a better technologist, because you have the knowledge of how photography can be used. Now here's a photograph that people will say to me, oh, I can do this in Photoshop. Pretty hard. You gotta think about it. The reason it's hard is because you don't know what's behind things. Photoshop only works with what's up front. But my area of interest over the many years has been high-speed photography. Here's a supersonic bullet cutting rubber bands in half. Time over this way, and obviously these rubber bands on this side have had a chance to spread out a little bit further than the ones closest to the exit. I used to fire guns in my classroom until the security found me out after 30 years of doing it.
Seriously?
We used to fly rockets in a room like this, smaller than this, into the ceiling, and make a mess of it. My lab was great. It smelled. Anyway, these are kind of fun photographs. So what I'd like to do now is to with your help, do a demonstration how we would go about solving a photographic problem that makes an event invisible because it happens too quickly. So we need an event. Well, I came with some. These are not high-speed events. Okay. However, there might be a high-speed event here somewhere. It's not a high-speed event, yeah? Okay, now I used to do what I'm going to do next without warning. But usually what would happen is people would get startled and elbows would go flying. People would scream, they'd fall out of their chairs. So I'm going to tell you now, I'm going to do something. What is it? Very good. So this is not a high-speed event either. The high-speed event was in between, right? When the balloon was breaking. So if I were to ask you, what did the balloon look like as it was breaking? I don't know. It happened too quickly. So that's going to be our project. Just to photograph the balloon in the process of breaking. And we'll see how we can do it with simplified equipment. The camera is going to be immaterial. Any camera, pretty much, can be used to do this. So, for a landing pad, and Anybody got strong lungs? Sure, you guys. Okay, we'll do a couple of these, all right? You do one, I do one. I'm going for a lung test on Monday. This is good.
How big you want?
So we can see the straight edge. Yeah. Yeah, that's good. Okay, so now we put this balloon here, this is gonna be our subject. And I hope I'm going to get a couple of volunteers to help me actually make the photograph, okay? Because I can't do all of the things at the same time. So be thinking about saying, yeah, I'll help with them. So I said, we're gonna make a photograph, so we'll get a camera.
Can we do cell phone cameras?
Cell phone cameras, maybe not. You put it on video. The reason is that in order to make the photograph, you do need to do it with the room lights dim, dark, and a significant exposure time. The cell phone cameras give you an instantaneous shot. Not of yours?
Not any camera.
That's correct. So this it's kind of neat because this camera, and many of these have a video out, okay? So you'll be able to see what we're seeing. And let's see if that works. Come on. Look at that. Wow, that's kind of distorted, isn't it?
Yeah.
Why is that?
TV.
Yeah, the TV. Wrong aspect ratio or something. But it doesn't matter. So we get a good picture of the balloon, we kind of focus it. All right, it tells us, what? F8, ISO 2000. Let's see. About 400, like 400. And we're going to be working on manual exposure. And so we'll set it to, oops, wrong way. A B, right there. And now we can ask ourselves pertinent questions. Joe and Sally are going to make a photograph of this. Sally's going to pop the balloon. Joe is going to operate the camera. And they decide to do it. What kind of problems do you think you're going to run across?
Timing.
Timing. That comes right at the top of the answer, right? There's another problem. Not quite so evident. But maybe one of you has insight on that.
Exposure?
Exposure.
Shaking the camera as you press the button.
Exposure time.
Shutters.
Because you realize this is a fast event, right? Now, if I open the shutter and blow up the balloon and then close it, I'll get a picture, but it'll be very blurry, right? So I need to make the photograph at such an exposure time that during the time that this is breaking, it won't appreciably appear to move. It'll be sharp. Right? It's easy to make blurry pictures of fast-moving objects, or any objects. How many of you make blurry pictures? And it's also easy to make sharp pictures of objects that are standing still, right? That's easy. What we want to do is the hard thing, which is making sharp pictures of fast-moving objects. Fast-moving object, sharp pictures. Now, we control sharpness with exposure time. The shortest exposure time on this camera is, I think, about an 8,000th of a second. But if we were to try to trigger the camera, we still have a problem. Timing. Remember, if this happened when that was breaking. Also, the 8,000th of a second is really not short enough to cause this to be blur-free. It takes this about a 500th of a second to disappear. Okay, so in an 800th of a second, half of it will disappear. So we need a shorter exposure time than the camera can deliver. Where do we get that? Anybody?
Video.
Yeah, video, no? Strobe. Or electronic flash. Strobe is a repeating flash. Electronic flash is a pop. And we got one right here. Yeah. There are other flashes that could be used. I like to use this one simply because I like to use it. And I've used the old Vivitar 283s and so sun packs, anything, any flash that can be operated at a reduced power. Okay, electronic flashes can be adjusted so that they give you a lot of light for a long time or a little light for a short time. So at a 64 power, which is where it's set, that flash duration is about 30 thousandth of a second. Well, that's quite a bit shorter than the camera can use, right? And not only that, well, it can do that. But we still have the timing problem, right? Not only that, but if we're going to use a flash to light the scene, we need to open the camera shutter, wait for the flash, right? So we get a dark in the room. So we got to do this in the dark. But we got the timing problem. This has to be fired when that is breaking. Well, that's a challenge, right? We can't do it manually. We know our synchronization ability is no good. So enlist help from electronics. You know, it's interesting that doctors, astronomers, and so on have photography as a hobby. But very few photographers have electronics as a hobby. That's a mistake. Because there's so many things that electronics can help you with in order to achieve photographic results that it should not be ignored. You know? But it doesn't happen. So we could go the high-tech solution, or we can go the low-tech solution. I like the low-tech solution. This cassette tape recorder has what we need. Who knows what a cassette tape recorder is? Anyway, the heart of this instrument has an amplifier in it and an output to magnets and to earphones. Okay? So there's an earphone jack so you can listen to what you're recording, and it's got a microphone as an input. And what this will do is when it hears a sound, it says, hey, I heard a sound, and I'll amplify it and I'll send out a signal. And the signal goes into a gadget which is built into this little hat. And it's a triac or a silicon control rectifier. It's just what you call a transistor. A special kind of a transistor. It's a switching transistor. So when you operate it, it closes a switch. That's just what the flash needs to operate. Close a switch. Well, let's see. So I said, this goes to the earphone. Put this over here. And plug the flash in here. And now if it hears a loud sound, maybe, a number roll, it flashes. Oops. Pretty good. Just what we need. Because we can put this microphone over here, right, and listen to the breaking balloon. And when the balloon breaks, causes a sound, goes down to there, flash goes off, but we have to have the camera shutter open at the time. So this time, what I'd like to do is to ask two of you to become one of them the balloon popper and the other one the camera operator. Yeah, two people. Come on, put your hands, show up, help. Oh, come on, guys. You too. Yeah. And well, yeah, I realize now why I need two, because normally I operate the lights, but once you operate the camera. But I do have a light assistant, which is pretty good. So all you need to do is to push down on this button, on this one, and hold it down until after the balloon pops. Okay. So the camera will sound like this. Okay. And Casey, when you hear the camera go open, okay, then you pop the balloon with the pin. Now, normally I like to do this demonstration, and it's kind of cute. I like to rehearse it, okay? And I will. What's your name?
Mike.
Mike, and I will tell you what the sound of what the camera sound is going to be when it opens. It's click. What is it?
Click.
Click. And Casey, when the balloon pops, it makes a sound. Boom.
Okay, good.
Boom. It's boom, right? So this time, before the lights go out, because when the lights go out, you won't be able to see what's going on around you. Okay? You'll just push down and it'll happen to you. Okay? So we will rehearse the events without actually doing anything. Okay? So I will ask you, Mike, to open the camera shutter, and then you'll go down on the button and the click, and the sound will be
Click.
very good. And then when you hear that click sound, you go, and then you go click again.
Click.
You'll lose. So presume that the lights are out. Mike, open the shutter. No.
Click.
Rehearsing. Boom. Mike, open the shutter.
Click. Boom. Click.
Very good. Now, this time we're going to do it for real. Lights out. Very good. And we'll see if you got anything. Well, we'll get something. However, one thing that we didn't do, and it's okay, is to adjust the response of the camera sensor to capture enough light to give us a better photograph, right? So we're gonna correct for that. We know how to do it. It's basic photography, right? More speed on the sensor, or what? Larger aperture on the lens, right? So we're going to change, what shall we do? We were,
What are you on now? Okay.
yeah.
Cool though.
Why don't we keep it at f8 and, oh wow, this was 22. Yeah, that's no good. So let's try the f8. Okay. So, and this time, try to hit it over here. And, oh.
What I heard.
Yeah, we got
It's not experience.
Yeah, work another one. Okay, so let's try this one more time. Lights out. Go ahead. Very good. Wow, look at that.
Oh, cool.
Oh, yeah.
I think your battery's dying on the camera. The battery symbol was up before.
Oh, yeah? All right. I have another battery. All right, so there we go. A balloon with a hole in it. Right? It's something that you actually couldn't see. It happened so quickly. But now we're going to put a little math in it. Okay? Remember I said it takes the balloon about a 500th of a second to disappear? Where did that come from? We could do that with high-speed cameras and stuff, high-speed video cameras. Cost a gazillion dollars. We are going to do it by knowing something about sound. We need to delay this next photograph a known amount of time. And how do we do that? Take the microphone, move it away, right? That will cause sound, that will cause a signal to get to the microphone later, because sound has to move the extra distance, right? Now, it would be good if we knew how fast sound moves. Anybody know?
600.
600 meters per second.
Yeah, I think it's around 300. No?
So-
Yeah, but in the foot system, or the royal system, it's about 1,100, 1,000 feet a second. Now, in elementary school, and you all might have taught your students about this, that you can tell how far lightning is by counting after you see the flash of lightning, right? It's a common teaching topic. So if you count to 5, it's a mile away, give or take. So it travels 5,000 feet in 5 seconds. Right? A mile is 5,200, whatever. 5,000 feet in 5 seconds. So that means it travels 1,000 feet in 1 second. How long does it take to travel 1 foot? 1,000th of a second. So we move the microphone about a foot away from where it was before, and we do it again. All right, you guys ready? Let's wipe that out, and get the camera ready, and do it again. Excellent. Very good.
That was pun in
So
there.
here we're the next one. Okay, guys, I appreciate your help. Mike, Casey? Excellent. We're not gonna need that.
You didn't,
The what?
you're not gonna need it?
Well, we'll do it.
Yeah.
Took all that effort. Anyway, we can now take this photograph and the previous one, which is like here, and this one, and compare the two. Obviously, the one where the microphone was moved further away is more broken, right? So now I would ask, Mark, if you could tell me roughly how much of the balloon has disappeared? A quarter. Mark says,
It looks like about a quarter.
he says it's about a quarter. It doesn't matter, right? It's the concept that's important, right? About a quarter, let's say the balloon has disappeared. And now we're going to take a look at this one, and I'll ask Matt,
Yeah.
how much of the balloon remains?
I'd say about a quarter.
Okay, remember, it's the concept that's important, right? So a quarter of the balloon remains here, and a quarter of the balloon has disappeared earlier. So how much of a change was there between the two pictures?
Half.
A half. And a half of it disappeared then in how much time? A foot? A thousandth of a second. A thousandth of a second, right? So if a half of it disappeared in a thousandth of a second, how long will it take the whole balloon to disappear?
2 thousandths or 1/5.
Or 1/500th, and that's where the 500th of a second, you took my word for it. It takes a 500th of a second to disappear. As I said, we could have used extremely sophisticated cameras and we would come out in the ballpark. And not two balloons break exactly the same. So we did a little photography, we solved the problem, and we applied some math and some insight as to how things work.
What other popular reactions can happen in the same kind of time frame besides breaking a balloon? And I can't bring a gun into my classroom.
Splashes, water drops hitting things, or milk drops. You use a slightly different way of synchronizing, but they would work. And they're very visually appealing, these little splashes, they're little crowns that happen.
And how do you trigger that?
Yeah, that's a little more tricky. Those, because the splashes don't make a sound, or much of a sound.
Big splash.
They're triggered by breaking a beam, a light beam. And then you put delay into it. So,
Breaking a light bulb would work? with
breaking
this
a
method?
light bulb, can you do that? Anything is dangerous in a classroom, isn't it? Flying glass and, yeah, it's tough. Splashes are neat.
Smashing watermelons.
Pumpkin
That
chunking.
works.
Pumpkin
I'm not
chunking.
gonna get into that. But anyway,
Pumpkin chunking.
I will provide through Mark a set of reprints or articles that I've written about this stuff.
What was your source for the triac trigger? Where
Radio
you made
Shack.
it?
Radio Shack.
For the actual plug or just?
Oh, the plug?
Electronics.
Yeah, the electronic part. Inside of here, unfortunately, is covered up.
Did you make it?
Yeah,
Oh, okay.
I make it all.
If you didn't have a strobe, what was a good strobe to find on eBay or something like that to use?
One like this,
With an external trigger?
with an external input, right. Let's see. Oh, I think I have a little bare one.
Oh, that's okay. I think it-
No, you can see it in here. That's, this one is encapsulated, there it is on the wire. Okay, we're gonna move on. Okay, was that it? Now, what are we gonna do? So, I think we're gonna do this. So, here's a subject that you might be asked to make a photograph of, or two or three, okay? Ping pong balls. Well, you know, a creative photographer, I don't know what they would do. Put them over there. And wake up now. So here we have our ping pong balls. And you might make a photograph and you end up with ping pong balls. I'm not saying that it's not very creative. It could be. But we want to do something other than a straightforward shot of ping pong balls. And maybe I can ask Mike to help me again?
Do you know what transistor this was? PNP, NPN?
I think it's an NPN, high sensitivity, 400 volt. I think it's an SCR. I'm sure it's an SCR. Triacs work probably better, but I haven't made one. So, I'm going to photograph this ping pong ball. I'm going to put some light on it. And I should get into over here.
Let's see.
And, this time, we'll do the same thing. What can we do? Okay, this time. So this time, I'd like to make something that normally, before we wanted to make a sharp photograph of a fast-moving event, right? Well, sometimes blurry photographs are just as useful as sharp ones. I'll demonstrate. You push that and let, open the shutter when I tell you to, and close it when I tell you to. Okay. Open it. Close it. Excellent. I say, oh, I could have predicted that, whatever it was. But, you know, this gives you a lot of insight into the behavior of a ping pong ball, right? It tells you that the ball is losing height with every bounce. In a physics situation, this could be important. How much height does it lose from bounce to bounce? Because depending on the material and the elasticity and the stiffness, you know, it'll all change. But you can see a number of other things. The fact that that the bounce is getting smaller. What else do you notice about this?
Shorter. The distance is shorter.
The distance is shorter? And what else? Oh, thanks, Mike.
No problem.
Maybe you'll come back.
Yeah.
But
I wanted to be out of the way from people.
Oh, yeah, good. So what else can you tell?
Slowing down.
Where?
The ball itself.
At the top.
At the top, it's slowing down, and you can tell that why.
It's darker.
The opacity changes.
How about its light?
Oh, yeah.
It's brighter, and it's going slower. And then it speeds up. So it's getting darker towards the bottom, where it's speeding up. And if you were to write a PhD paper, you could write up an analysis that would describe how fast the ball is traveling based on the brightness of that trace. And it's not a trivial problem. It's not a trivial problem. But normally you wouldn't do that, because it's too difficult. PhD. Easy. So we can tell something about the height. The thing is that we can tell is how fast that ball is traveling. Why? Yeah, no time base. We do know, we could determine, for example, how much height it loses from these traces, but we need a scale. We don't have a scale. Or do we?
2-second shutters?
No. A height. We need a measurement of height. What is it? The scale is right in my hand. The ping pong ball is our scale. You know, we measure it and we say, oh, that trace is an inch. So from here to there is how many ping pong balls? And we get our answer, right? So it's useful sometimes to remember the scale can be the subject itself as long as you take trouble to measure it beforehand. Just to think about it. The neat thing about including a scale in the picture, okay, or the subject itself is the scale, you don't have to put rulers in there that are not in the same plane as your subject, and then you have to say, well, the ruler is 12 inches behind, and you can make adjustments. Use the subject as your scale, I think. So we don't have a time base to determine how fast this thing is traveling. Let's think about a time base. How am I going to do that? Well, we can include a time base by using something rather simple. A stroboscope. I have a gazillion-dollar stroboscope right here. Physics labs are getting rid of them. They don't know what to do with them, many of them. And they're sitting on shelves and stuff, huh? They're very useful stuff. But they're outside of the reach of most students. And most teachers sometimes. I'm talking about, well, on eBay, maybe $500. If you're lucky, $75. But originally like $5,000. You don't need that to do an experiment. I'm suggesting a mechanical stroboscope is what you need. And this is one of them. It costs like $5 to make. A little electric motor, some stiffened cardboard there, and a rotating disc that's attached to the motor. So this spins, and there's a slot in it, okay? And every time the slot goes past the opening, the camera sees a picture. Okay, so all we're going to do is attach this to the lens. That's the most difficult part. Right. Let's see. I came with triple backups here. Yeah, but neither of them is the right one. So I'm going to rely on my fourth one, which is on the top. Here, Jingo. Come on. All right, good job. Okay.
Care flowers.
That's the problem with lenses that come in multiple filter dimensions. Nothing fits on anything. Okay, so we put our adapter on there. Like this. Spin around here. Wow, it went on real well. Now, this motor turns that disc at a variety of speeds. And it can be controlled with the battery pack. Like this. This is 12 volts. This will go pretty fast. But I can put this camera on display like I had before. And let's see. Let's see what happens as this one turns. Not much. how about if we put some light on air? And actually, we should put something that the camera can see. All right. So it just sees the balls over there, right? Now the only difficulty with this, it's a little heavy, so I brought a, where is it? A little variable power supply. It doesn't put so much strain on the cable, that's all. But the idea is the same. Okay, we're going to turn that. And we can change the voltage. So we can make it go slowly, and we can make it go quickly. So we can go like that. And we tried to make this a pretty picture and put light on both sides. So, Mike, you can help me again. And I think we're going to do the same thing. So open the shutter. Okay, hold on. My bad here. I didn't hear it, so, but this time I'll hear it. Okay. Open the shutter. Close it. Excellent. Oh, we don't have enough light. Great. So, let's go. Let's go on ISO. Raise it.
How can you raise your ISO versus changing the f-stop?
I don't know, it's too complicated.
Okay.
Okay, we'll try it again. Open. Close it. Yeah, I didn't go too far, but. Oh, not pretty enough. Let's try it again. I like it when it's pretty. Open. Close. Oh, all right, that's better.
Okay.
Oh, okay, great, thank you. So, you know, that's pretty good, if I say so. Because we can, now not only do we have information about the change in height, but now we know that in this amount of time, the ball moved a certain distance, which is, we can measure from this number of ping pong balls it's fitting, right? Now making a picture like this was pretty difficult in the past. You can use an electronic flashing light, but that's typically pretty expensive. This is easy to build, easy to apply, and you can learn an awful lot, physics out of it, mathematics out of it, and what else can I say?
Is there a way for you to determine
Oh, yes.
the timing?
Yeah, good question. See, I forgot about that. That's the one thing that we're missing. We know that there's a difference in time, right? But what we don't know is how much. Feed you again. And what did we put that? Put it in here. Excellent. So this time, what we're going to do is to not use, might just open the shutter, right? This time, we're going to open the shutter for a known amount of time. The camera's timing mechanism, shutter mechanism, is quite accurate. I mean, these people depend on making sure that if you say it's 100th of a second, it's 100th of a second, right? Now, in the old mechanical age, that was not always so. But in the electronic age, with crystal controlled oscillators and stuff like that, timing is very, very good. So we're gonna choose a time. And how about we choose a quarter of a second. Okay? And this time, Mike, you're gonna have to react to the ball flying instead of me telling you to open it. So as it's bouncing, okay, you operate the shutter. Okay. Okay, how about, I think you get the gist of what's happening, but let's get a few more images of that ball. And we'll choose a longer exposure time. Half a second. Yeah, you reacted a little too fast. Let's try it again. Okay. So, take a look at this. There you go. So it was a half a second. And in the half a second, we got 1, 2, 3, 4, 5, 6, 7, 8, 9 images of the ball. Now, we can quibble a little bit about this, but so if in a half a second we got 9, in 1 second we would get 18, right? So it's running 18 RPS. The difference in time from here to here is an 18th of a second. Did I do something wrong? There is an error that can creep in here, and that is that we could have just missed that ball. So there is, a little error, but the more images you get, the less that error might cause a problem. So we can vary the speed, of this thing, so we get more, less. It's a nice little instrument, photographic, physics, mathematics, all kind of blended into one. And this demo area right here is terrific. It's the best that I've ever had. Because one thing that happens is if you don't have a really good black background, it tends to bleed through your images because the exposure times are long. Anyway. So I did bring a project that I've never demonstrated to an audience. And I hope that you are willing to put up with an experiment instead of a finished product. How about it?
Yep.
Yeah.
You're willing to live with an experiment. All right. So still leave the camera. Switch lenses. Oh, yeah. Pass it around.
How did you determine the width of the slit?
Yes. It felt good. Yeah, about 5 degrees or so, maybe a little bit less. The finer you make the slit, the sharper the individual pictures are going to be, but also the less light you get. It's a common thing. The shorter the exposure time, more light you need. So, okay, Mike, I think you can sit down if you like.
Gotcha.
Now, what am I going to do? Okay. That's interesting. Oh, yeah. So, in high-speed photography, one of my interests has been, and it kind of served me well over the years, was to concentrate on photographing through slits. Over here, it used to say, there it says, looking at life through a slit. So, I'll show you what's in here. got? Black box with a slit on one end. Yeah, right there. So we're gonna take this and attach a camera here first. And this is essentially a turntable, a camera rotation gadget. You can make this camera pan to the right or to the left. And for that, this power supply will work. I think. Battery power will do it. Okay, so that's the whole function of that. It turns out that those little gadgets are pretty expensive now. But, fear not, you can do that by hand. If you don't have a mechanical thing like that, or electronic, you can rotate the camera by hand. We don't have much time, so I'm going to go directly to doing it this way. So this goes in here. So I'm putting the slit right in front of the camera lens. And I'll put the soap gadget on a turn. Now, I'm going to get to see the view through the camera lens. Right? So connected, this is up. Live view, you should see something. Oh, it's that. Just what we're hoping for. Interesting. And so, now, if the camera rotates, you'll see what happens to that slit. It wipes across the film gate, right? Okay. Now it's a powerful thing because it is all about time. Now, one thing which is useful if you do this is to rotate the camera about the center of rotation of the lens. Some people call it the nodal point, other people call it something else. Obviously. I should be able to see the whole. There's the whole slit. And the size of it is small, but we can make it even smaller with a small aperture, because then the depth of field of the lens is such that this and whatever we're going to put out there is also included. So let's see what we can do with this. All right. We're building up to something. So let's see what happens. If we move the slit to one side. Okay, and now open the shutter. And then move it back to that side. Oops, went the wrong way. Oh, you we can't see it while it's doing it, we can only see after the results. And we have a bunch of streaks. And I can't do anything with streaks. Let's see. Too short next to what you're talking about. Okay, make it go fast. Oh, just horizontal bands. They represent whatever the brightness of the subject out there is, spread out over time. Oh, what can I do with this? Well, I'll show you. And I'm gonna need, maybe Mike, you were such a good helper, maybe you can help me over here. Again. So what I'd like you to do is to put your hand over here. You'll get on this side. Well, let me just take and see better if you get on that side. And you'll be waving your hand up and down like this, okay? But let's first of all find your hand on that slip. Can we see it there?
Yep.
Yeah. We might want to put a little light on it. So I have an auxiliary right here. It's not as bright as that is. Yeah, I got to, see it. Plug up. And, oh yeah, like that. Still kind of sort of holding together.
Should I turn out these other lights?
Yeah, that would help. What happens is the camera's sort of going to stay open, so any light in the room leaks into the black box. And while it's not significant, sometimes it is. So by keeping the light out here, or putting a dark cloth, it would be even better. But now, we realize there's his hand, right? So this time, yeah, wave it up and down. Okay. And what I'm going to ask you is to tell me what the frequency is that he's waving his hand at. Okay, you can sit down for a sec. Stick around, maybe I'll do it again.
Not to cut things short, guys, but the last shuttle will be running in the last 15 minutes, so if you have to get to lot 7, I advise you to start heading up relatively soon.
So, what this has become is an optical oscilloscope. You all know what an oscilloscope is, right? It monitors changes in voltage, resistance, and so on. It displays them on the screen. Horizontal dimension is time. Vertical dimension is amplitude. So here, this is an optical oscilloscope. We look at one line, we spread it over the film, over the sensor, and if we knew what this time was, we would be able to tell what the time was for one cycle. How do we do that? Well, we include a timing device. I have them here. And I suggest that these are also very useful to make. I can find it. Here we go. It's an LED, and a battery, and some full circuits. Okay. Now watch what happens here. See the green dots are spaced out over, right? Are they spaced out? Right. They're flashing 100 times a second. 100 times a second flashing. That's pretty good. Because we're going to put this, and can you stay a second?
Yep.
Put that in the field of view of the camera. Move the camera back to the middle. So we can see this. First of all, we're gonna have to adjust that so it's on the slip. And, oops. Okay, and now move that back and forth until we can see it. Look, is that it?
Yeah, that's it.
Okay.
So
So,
the last shuttle is heading out in just a few minutes, if you need to catch it to the parking lot.
okay, one shot.
Here's my name.
Yeah, and this time, we're gonna do a little faster. Wave it faster. Oh, yeah, it would be helpful if I had the shutter. Okay, there we go. Now, we get that green band there. Let's take a look at that. It's there. Oh, let's look at it in detail. Down there. Ah, look at that. There's your timing. 1/100th of a second between these, and then if you look at the whole picture, you can say how many hundredths of a second it took for the one cycle, and out of that comes cycles per second. And have a good trip. I'm sorry the bus is leaving. Take care.